What's up, scholars? Mr. Ipshon here. Today we are going to continue our unit on work, energy, and power. Today we're going to define the physics definition of power. Power is the rate of transfer of energy. In other words, power, which we usually use the symbol P, is the amount of energy transferred, or delta E, per unit time. So I think that's how it's written on your equation sheet for AP Physics. And what's nice about power is it can be sort of carried around and used very generically. Here, this energy is any kind of energy. So we could be talking about electrical energy, we could be talking about potential energy, we could be talking about kinetic, we could talk about nuclear energy if you'd like. So in general, power is defined as how much energy is transferred per unit time. Let's look at the units for power. So that would be defined as, well, we know that energy is joules. Time is in seconds. So 1 joule for 1 second is equal to 1 watt. Put that in brackets. We usually do that when we're doing units. So 1 watt, that's the SI unit for power. It's named for a person called James Watt, who helped invent the steam engine long ago. All right, I want to make a very important distinction. So I've written the word important. Power is not the same thing as energy. Specifically, power is the rate that we're transferring energy. But here's what I mean. A lot of times when we talk about, as an example, when people will talk about like power plants, whether it be coal or nuclear or anything like that, you'll see the words energy and power thrown around in a bunch of different situations. So I just want to clarify and talk about some of the units and why they can be so confused. I want to do a classic example to try to illustrate the difference between energy and power. I'm going to use an incandescent light bulb to do it. So you're probably familiar with sort of this style of light bulb with the filament, and physics teachers love these because the sort of generic version of that is 100 watts. So let's go ahead and draw that. Of course, nowadays, most people don't use incandescent bulbs for most things around their house. We've sort of started to convert to mostly LED bulbs or compact fluorescents because they're much more energy efficient. And we're going to talk about efficiency in just a moment. But anyway, the question we want to ask is, how does IPL calculate our electric bill? So how does the electric company calculate our electric bill? You might be able to imagine a handful of ways they could do it. One way they could do it that would just be maybe really easy to do and wouldn't take a lot of effort on their end is count how many electrical outlets people have and charge them, 10 cents, you figure it out. But they could just do it by electrical outlet. They could do it by how many appliances you have, but what they actually do is they measure how much electricity you're pulling off of the grid. So we're going to use our 100 watt light bulb and just imagine that's all we have running in our house, and we'll try to calculate for a typical month how much this light bulb would cost. So I want to be careful and say that the way that the electrical company does this is that they look at how much energy you used through all of the devices that you powered in your home. To do that, to figure that out for a 100 watt light bulb, we're going to make a few assumptions. We're going to say it's a 100 watt light bulb and it's going to be a constant wattage. The bulb is on for 10 hours a day. It's just going to make the math a little bit easier. On for 7 days a week, and a month has 30 days. So what we want to calculate is how much energy. So energy is going to be, if we take our equation, it's going to be power times time. That's how much energy we're going to get here. Power times time. So what we need to do is work out how many seconds, that's measured in seconds, are in a month for 7 days, 10 hours a day, and times that by 100. So we've got our scheme. We just need to find the time, and the first thing we need to do is find the time in a 10-hour day. So that'd be 10 hours times 60 minutes per hour, and you're probably comfortable canceling our units there. Okay, times 60 seconds per 1 minute, cancel our units there. And this is why I made it 10 hours. It's just kind of arbitrary, but that's 3600 times 10, 36,000. And that is seconds. Now, to get the time in a week, we need to multiply that by 7, and the time in a month. So we'll say time in a month is 36,000 seconds times 7 days in a week, days per week, times 30, oops. Many of you were probably way ahead of me. I actually don't need 7 days per week because we already have 10 hours a day, and we're going to just assume that's for 30 days. So all we need to do then is multiply by 30 days, and voila, we've got the total number of seconds in 1 month if we're just doing 10 hours a day. So 36,000 times 30 ends up being 10/8 with 4 zeros. Yeah, 10,000 seconds. Okay, fantastic. So what we're going to do is we're going to punch that in to energy, and we're going to see what we get. It's going to come out kind of weird. So we're going to have energy is 100 watts times this number of seconds. So that's 10.8 times 10 to the 6 seconds. I'm being lazy here. So we end up with, add one up there, 789, 1.08 times 10 to the 9 seconds, so, or watt seconds. So 1 billion watt seconds is the answer. Now, the electric company, in fact, does not bill you in watt seconds. They use kind of a weird contrived unit, which is the kilowatt hour. Now you can see in this that you've got a unit for power and you've got a unit for time. So this is actually an energy unit. Alright, so we calculated that over the course of our month that we made up, we do about 1 billion watt seconds worth of energy, and then to convert that into kilowatt hours, which is how we're normally billed, we need to divide by 1,000 to cancel our watts, and we need to divide by 3,600 seconds to cancel our seconds, and we'll be in kilowatt hours. So let's do that. I just did that calculation. You get exactly 30 kilowatt hours when you don't do any rounding at all. So to the power company, that's how much of their energy you took. Again, that is in units of energy. You're doing power times time. How much does this cost? Well, I did some digging, and I have my own electricity bills, but according to IPL's website, it's about 11 cents per kilowatt hour for the average customer. Here's what I found. Total monthly average bill is about $109, and depending on your plan, you're somewhere between 9.5 and 11 cents per kilowatt hour. So if we work that out, we would just do 30, because we did 30 kilowatt hours, times 11. So that would be, well, I'll do 0.11 so that we're in dollars. So this would cost you $3.30 for a month. So you might wonder, why does the average electricity bill here in Indianapolis, why is it $109? I just ran this light bulb for a whole month at 10 hours a day, which I don't normally do. Well, keep in mind a lot of your appliances, like your furnace, your water heater, heating and air conditioning, things like that, those are much more energy intensive, and those are on all the time. So another really important concept when it comes to both energy and power is the concept of efficiency. Efficiency is just a measure of how much useful work we get out of something divided by how much work we put into it. Or, because the t's will cancel, you could also say it's the power we get out per amount of power that we put in. So I wanted to look up what the efficiency of humans is, so how many calories we put in our bodies, how much useful work do we get out. According to this possibly disturbing thing from University of San Diego called MPG, miles per gallon of a human. They say that we're about 25% efficient. Let's just take that number at face value just to see what that means. So that would mean that the efficiency would be, let's say that I eat a 100 calorie, I'm going to put a capital C for food calorie in. That means that if I eat a 100 calorie candy bar, I only get 25 calories out. So I am 0.25, or you could say 25% efficient. Now, you might wonder, well, where did all 75 of those other calories go? You have to keep in mind here, when we talk about the useful work, I'll write that in red here, this is useful work. We're talking about sort of like macroscopic work, like I can use that to pick up items. But the other 75 joules worth of, or let's say calories worth of energy is going to sort of microscopic things, like the work done inside of my cells so that my muscles will work, so that my heart will beat, so that my blood will pump, so that my brain will work. Actually, a huge portion of your calories go to just fueling your brain. So while losing 75% of the energy to not picking things up and moving things around is necessary, what we say is that it's the excess energy is converted to heat. And what we mean by that is it's not useful energy that we can actually do stuff with, but it didn't disappear. It's now very slightly warmed my body, or it's warmed my environment. It has spread out into the universe. We call this concept of heat sort of dispersing from the very compact candy bar that we had into the universe. We call this the idea of entropy. Entropy. That is the idea that over time, the amount of heat in the universe increases. I am very much paraphrasing what's called the second law of thermodynamics. You've also probably heard of entropy from chemistry classes, but for right now, this is all you need to know, is that the law of entropy essentially says that energy tends to become less organized in open systems unless work is done. So as an example, once you heat up a cup of coffee, it tends to cool off, and the original amount of energy, which was quite localized and organized in the cup, is now going to spread around the room. So, to wrap this up, we're going to talk a little bit about energy units. So you might see, and we talked about energy being measured in joules. If you take 4.184 joules, that's the same as 1 calorie. That has a chemistry definition found right here. So that many joules of energy is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. There you go. Anyway, that's why you see calories used. Now, to be clear, this calorie is not the same calorie I was talking about before. So 1 lowercase calorie, or let's say 1,000 of those calories, is called a kilocalorie. Or in America, we usually just write it like this. Oops, so that's 1 kilocalorie, or 1 C big calorie. So it can get a little confusing if you've ever traveled overseas or to a different country. A lot of times you'll see labels that are maybe slightly confusing, like this one. So I think this is for some orange juice. You can see the energy is represented in both kilojoules. So this, if you had a glass, a 100 milliliter glass, that's 224 kilojoules of energy. Now, we're not used to that. We have no idea what that means. That's 53 of our calories that we're sort of used to. And 250 milliliters, which would be more like an 8-ounce glass, that seems like a more reasonable 132 food calories. Sometimes that big C is called food calories, or sort of strangely 561 kilojoules. I say strangely, it's just odd to me because I'm not used to it. There you have it. I think one of the things to take away from this brief set of notes is that energy and power can be a little bit confusing. Just always go back to the definition. Power is the rate of transfer of energy. And so if you want to do any calculations, just keep your units straight, like you saw down here, and just know which units you're working in. So are you working in joules? Are you working in calories? Are you working in kilowatt hours? Or are we working in watts? It depends on which thing we're talking about. Thank you so much, scholars.